Welcome to my lecture on cold atoms. Today I want to discuss a very elementary situation which we encounter in many of our experiments. An ideal gas is trapped in a three-dimensional harmonic potential. We assume thermal equilibrium at temperatures just a tiny little bit above absolute zero. Here we are talking about millions or even billions of a degree on the Kelvin scale. And we are interested in the energy distribution as well as in the distributions of the particles in position space, velocity space and phase space. Considering the phase space density will also connect us finally with the quantum world of degenerate gases. Let me start with a situation usually considered in textbooks. A three-dimensional box potential in which particles are confined between hard walls. From the equipartition theorem we know that, on an average, a particle has an energy of 3½ kBt, where kB is the Boltzmann constant and T, of course, the temperature. Each degree of freedom, as we know very well, contributes 1/2 kBt. Within the box the situation is homogeneous, with the number density simply given by the total number of particles divided by the volume. In contrast, what we usually have in our laboratories is a three-dimensional harmonic trapping potential. The mean energy per particle now is 3 kBt because in harmonic oscillator potential energy gives the same contribution as the kinetic energy. Now we encounter an inhomogeneous situation where the number density is a function of the position. How can we describe these inhomogeneous density distribution? Let's consider some basic statistical mechanics, and here's a question for you. What do you think is the most powerful tool of statistical mechanics? The most powerful tool of statistical mechanics, to my opinion and to the opinion of many textbook authors, is the Boltzmann factor. For a system in thermal equilibrium, it says that the probability of a system to be in a certain state is proportional to an exponential factor governed by the ratio of the state's energy E to the thermal energy kBt. And this generally applies to single particle states as well as to microstates of a many particle system. The Boltzmann factor allows us to calculate the occupancy of states in the trapping potential. We consider an ideal gas of n atoms and want to know how they occupy the single particle states of the trap. And here is what the Boltzmann factor tells us. The occupancy is defined as the average number of particles in a single state, here with an index I, and C sub I are the corresponding coefficients. C0 appears as a proportionality constant and corresponds to the occupancy of a state with energy 0. Now we can calculate the total number of particles by summing up the occupancies of all states. The resulting normalization condition connects the particle number n with the coefficient C0. Let me note that C0 is much less than 1 in the classical non-degenerate regime. Now I come to another interesting question. What is a single particle state in the trap? In quantum mechanics the answer is rather straightforward. It is a motional quantum state of a trapped particle. In classical mechanics, this corresponds to a 6-dimensional phase space cell with a volume given by the Planck constant h to the third power. For a large system supporting many states, the discreteness of quantum states can be neglected and the system can be described as a continuum in phase space. The correspondence between classical and quantum mechanics is established by our choice of h cubed as the volume of a phase space cell. And now we want to know how the particles are distributed in phase space, and we look at the occupancy of the phase space cells. We consider a large classical system with many states and express the occupancies as a continuous function, which simply is the Boltzmann factor with a proportionality constant. In this way we introduce a quantity, ρ, as a function of the position r and the momentum p, which we call phase space density. Representing the occupancy of phase space cells, it is defined as a dimensionless quantity. The proportionality constant ρ0 represents the occupancy of the ground state with energy 0, and we call this maximum occupancy peak phase space density. In the non-degenerate regime, it should stay much smaller than 1. Finally, we consider the normalization condition. We obtain the total number of atoms n by integration over the 6-dimensional phase space. To get a number out when integrating over r and p, we have to divide the integral by h cubed. This normalization condition connects the peak phase space density with the number of atoms. But how about the energy in 6-dimensional phase space? What is E as a function of r and p? As we know very well, the energy separates into kinetic and potential energy. The kinetic energy depends only on momentum, not on position, and is thus independent of the trapping potential. In contrast, the potential energy depends on the position and thus on the particular trapping potential. Let us consider the 3-dimensional harmonic trap, which in general is anisotropic with different confinement along the principal axis x, y and z. With the corresponding trap frequencies omega x, omega y and omega z, the potential energy can be written as E pot equals 1/2 times the particle mass m times omega x squared times x squared, and the same for the y and z direction. And here is a useful definition. In many cases, we just have to consider the mean geometrically averaged trap frequency, omega bar. You will see this quantity in many equations in the following. And now we have everything complete for describing the energy in the 6D phase space of a 3D harmonic trapping potential. We see that the energy is a sum of 6 contributions proportional to the squares of the 6 phase space coordinates. Let us now consider the Boltzmann factor with all its contributions from kinetic and potential energy. We define standard deviations in momentum and position space, sigma p for the momentum spread, which is independent of the direction, and sigma x, sigma y and sigma z for the spreads in the different directions of a generally anisotropic harmonic trap. Now the Boltzmann factor becomes a product of 6 Gaussian factors which all look similar. And this separation into 6 factors is a great simplification for carrying out integrations to determine the various distribution functions, which describe density profiles, the energy distribution, etc. Let us now look at the phase space density ρ0 in the trap center, where the energy is lowest, and let us show how it is related to the total atom number n. Here we have to integrate over the whole phase space, and we take advantage of the separation of the Boltzmann factor into 6 Gaussian factors. The problem just separates into 6 integrals, all with the same structure. And here are the 6 corresponding factors, and the result is here. To simplify this expression, we replace the Planck constant h with the reduced Planck constant h bar, and we introduce the mean trap frequency omega bar as defined before. And we finally arrive at this very important relation, which allows us to calculate the peak phase space density for a given trap frequency and temperature. Note the scaling with the third power of omega bar over t. A reduction of the temperature by a factor of 2 results in an increase of the phase space density by a factor of 8. This is due to a reduction of the spread both in momentum space and in position space. This equation here is something we use very often for analyzing our experiments. We have seen how important knowledge of the phase space distribution is, as it tells us how many particles can be found in a certain region of the phase space. For the three-dimensional harmonic trap, we have shown that it factorizes into a peak value, the momentum dependence and the position dependence. This equation shown here forms our basis for deriving other distribution functions of interest. For example, the spatial distribution can be obtained by integrating out the momentum dependence. Let us do it and derive the number density distribution. And here is the corresponding integral over the momentum space, which will give us the spatial distribution of the number density. We substitute the function ρ of RMP using the phase space distribution of the 3D harmonic trap, as discussed just a minute before. These three position-dependent factors are independent of the momentum and can be pulled out of the integral. The remaining task is then the integration over these three Gaussian factors, as we have exercised before. And here is the result, the three-dimensional Gaussian number density distribution of the harmonically trapped gas. By further spatial integration, we obtain the relation of the peak number density with the total number of atoms n for a given mean trap frequency and temperature. This is another important equation that we often use in our daily laboratory work. Let us illustrate the spatial distribution in the harmonic trap along one direction, say the x direction. The important quantities are the peak number density n0 and the width of the cloud, the latter being characterized by the standard deviation sigma x. And here are again the formulas how to calculate these quantities from the trap frequencies and the temperature. Sometimes in the literature you will find a quantity called mean number density, in contrast to the peak number density. It is useful as it characterizes a typical density, and this integral here defines it in a general way in principle for any trapping potential. How to understand this definition of a mean number density n bar? If we divide the number density by the total number of atoms, we get a probability distribution for the position of single atoms in the trap. In the integral, this now enters as a weight, so we calculate the number density weighted by this probability distribution, and this is why we get n squared in the integrand. Let's now apply it to the three-dimensional harmonic trap with the Gaussian number density distribution discussed right before. We use the relation between total number n and peak number density n0, and we carry out the straightforward integration, and we finally arrive at the result that the mean number density n bar is by a factor of square root of 8 less than the peak value n0. The difference amounts to almost a factor of 3, and it is important not to confuse these definitions. Now it is time for a realistic example. We consider a sample of laser-cooled rubidium atoms loaded into an optical dipole trap. We'll discuss the trap, very common in our field, in another lecture. Here let me just say that it's a focused laser beam, usually operating in the near infrared. You can also call it an optical tweezer for atoms. We typically load 10 to the 5 atoms. The trap is cylindrically symmetric with a trapping frequency of 1 kHz, characterizing the tight radial confinement. Axially, along the laser beam, the confinement is much less with a frequency of about 30 Hz. For a temperature of 10 microkelvin, rather easy to reach for rubidium atoms with standard laser cooling techniques, we get a velocity spread corresponding to a standard deviation of about 30 mm per second. We can now calculate the cloud size by dividing the velocity spread by the respective trap frequencies. The cloud is about 5 micrometer wide and more than 160 micrometer long. It has the shape of a cigar. For the peak number density, we obtain 1.6 times 10 to the 12 atoms per cubic centimeter, and for the peak phase space density, we obtain 3.3 times 10 to the minus 4. As we have discussed, the latter corresponds to the occupancy of the quantum mechanical ground state, and we see that we have a classical Boltzmann gas still far away from quantum degeneracy. There is another very important distribution which we have not discussed yet. I want to show now how one can derive the energy distribution from the phase space distribution. For a harmonic trap, we have shown that the energy is given by the sum of these 6 terms, which are proportional to the squares of the 6 phase space coordinates. For convenience, let me define 6 corresponding coordinates S1 to S6, the squares of which have the dimension of energy, and I can now, in a very simple way, define a hyperradius in 6D phase space. With this definition, one sees the wonderful hyperspherical symmetry in phase space, and the energy is just the squared hyperradius. Isn't that simple? For comparison, just note that in a box trap, the potential energy contributions corresponding to S4, S5 and S6 are absent, and the problem is spherically symmetric in 3D momentum space. The question I'm asking now is how many states exist with an energy below a certain energy E? To answer this question, we just have to calculate the phase space volume of a hypersphere with radius S, and here is the corresponding integral. With substitution of the phase space coordinates P and X by our definitions of S, we rewrite the integral in this remarkably simple form. And now it is easy to see that the integral corresponds to a so-called 6-ball, which is a volume included by a 6D sphere. We arrive at this result where S to the power of 6 can be replaced by the total energy to the third power. Finally, we obtain the number of states below an energy E by this expression. And this leads us right away to the density of states. We want to know how many states are contained in an infinitesimally small interval. The derivative of the total number of states defines the density of states function. For the 3D harmonic potential using the function n of E as derived before, we obtain the density of states proportional to E squared. And this is another important formula you should know when dealing with harmonic trapping potentials. Now we are prepared to introduce the energy distribution function. It is simply a product of the two functions describing the density of states and the occupancy of states. Just recall the expressions for the 3D harmonic trap derived before. Putting things together, we arrive at this energy distribution function. For energies far below the thermal energy, it increases proportional to E squared. And for high energies above the thermal energy, it falls off exponentially. Note that the Planck constant drops out of the problem. Yes, we are in the classical limit without any quantum physics. You can also check that the integration over all energies gives the total number of atoms, fulfilling the usual normalization condition. Remember the first slide of this lecture. I have introduced the mean energy per particle, which should be 3 kBt for the 3-dimensional harmonic potential. Let's see whether we can reproduce this result based on the energy distribution function. We have to solve this integral corresponding to the expectation value of the energy for a single particle. This is easy to do, and we indeed obtain the result that we expected based on the equipartition theorem for 3 degrees of freedom, which count twice for the harmonic potential. Let me summarize the main properties of the energy distribution function. The mean energy per particle is 3 kBt. For low energies, the function increases proportional to E squared, and for high energies, it falls off exponentially. Let us now go back into phase space, and there is something more I would like to tell you. I will now introduce a local phase space density, which is different from the general definition of the 6D phase space density or the peak phase space density in the center of the trap. We again start from the Boltzmann factor with the peak phase space density ρ0 as a prefactor, and we separate the energy in the exponent into the contributions by potential and kinetic energy. The first part here corresponds to the case of zero kinetic energy and depends only on the position. We call it local phase space density. I keep on using the symbol ρ for this definition of the phase space density, but only with the position r as the argument. Now let us get the number density from the phase space integral, where we integrate over the momentum. Substituting our definition from the line before, we obtain this integral, which we know how to solve. From this we obtain the relation between phase space density and the number density locally. That means at a certain position in the trap. We see that the local phase space density, as a dimensionless quantity, is obtained as a product of the number density and the volume governed by the temperature of the sample. We refer to it as a quantum volume lambda cubed, where lambda corresponds to a length scale below which the system goes quantum. Having much less than one particle in that volume, or in other words having an interparticle distance much larger than lambda, means that we are in the classical regime. The quantum length scale lambda is very important, and it is usually referred to as thermal de Broglie wavelength, and it corresponds to the matter wavelengths as calculated with the thermal momentum as defined here. It is named after Louis de Broglie, who received the Physics Nobel Prize in 1929 for the discovery of the wave nature of the electron. With this definition we can write the dimensionless local phase space density as n times lambda cubed, the product of number density and the quantum volume. Note that n and ρ are generally position-dependent quantities, while lambda is essentially determined by the temperature. And again, for a phase space density ρ far below 1, we are in the classical world. With ρ approaching 1, the individual matter waves start to overlap and quantum statistics becomes important. Then it makes an important difference whether the individual particles are bosons or fermions. And this leads to a strikingly different behavior in the world of quantum degenerate gases. Let me quickly summarize what we have learned about the differences of a gas in a harmonic trap as compared with the textbook situation of a box trap. While the box is characterized by a volume V, the harmonic trap is characterized by the mean trap frequency omega bar. Within the box the situation is homogeneous and the density profile is flat. In the harmonic trap, in contrast, we have an inhomogeneous situation with a Gaussian density profile. In a box, the number density does not change with temperature. In contrast, in the 3D harmonic trap, the number density is proportional to T to the power of -3/2. For the phase space density, this temperature dependence is even more pronounced, with the T to the power of -3 behavior. For the mean energy per particle, we get 3½ kBt for the box and 3 kBt for the harmonic potential. Finally, there is an important difference in the density of states. In the box, it goes with the square root of E, whereas in the 3D harmonic potential it is proportional to E squared. We have reached the end of the lecture, and I hope you have learned something useful for working in the lab with cold trapped atomic gases. See you in the next lecture.